Hi, myself G. Tharanitharan. This is the seventh video series of additive manufacturing and its type. Now we're going to discuss about the very important method, robo casting method of additive manufacturing. This is an ancient method as like stereolithography. It's a direct ink writing and other extrude based 3D printing technique in which the filament of the paste-like material is extruded from the very small nozzle and nozzle is moved across the platform. The object is thus built by the printing the required shape by layer. This technique was first developed in United States in 1996 as mentioned to allow the geometrically complex ceramic green boundaries to be produced by the additive manufacturing. In robocasting, a 3D CAD model is divided up into a layer in a similar manner to additive manufacturing process technique. This material is then extruded through the small nozzle as the nozzle portion is controlled, drawing out the shape of each layer of the CAD model. The material exits the nozzle in liquid-like state but retain its shape immediately, exploring the rheological property of the shear thinning. It is a distance from the fused deposition modeling as it does not rely on the solidification or drying to retain its shape after extrusion. Almost now I'm going to explain this process behind the robocasting. Robocasting begins with software process. One method in importing the STL files and slicing the object into a layer of similar thickness within also diameter. The part is produced by extruding a continuous filament of material in shape required to fill the first layer. Next, either the stage is moved down or nozzle moved up and next layer is deposited in the required pattern. This is repeated until the 3D part is complete. Numerical controlled mechanisms are typically used to move the nozzle in calculated toolpath generated by computer-aided manufacturing of software packages. Step-out motor or servo motors are usually employed to move the nozzle with precision as fine as nanometers. This part is typically very fragile and soft at its point. The drying, debinding, and sintering is usually followed to give the part of the desired mechanical properties. The part, depending on the material composition, the printing speed and printing environment and robocasting can be difficultly deal with more moderate overhangs and large spanning regions many times the filament diameter in length where the structure is unsupported from below. This allows the intricate periodic 3D scaffolds to be printed with ease, the capabilities which is not possessed by the other additive manufacturing technique. This part have shown extensive promises in the field of photonic crystals, bone transplants, catalyst supports and filters. Furthermore, supporting structures can also printed from the aggressive materials which is easily removed. This allow the almost any shape to be printed if any orientation. Next, I'm going to explain about the mechanical behavior of those components. One key advantage of robocasting additive manufacturing technique is usually in the ability to utilize the wide range of feedstocks, inks as shear thinning ability to the only inherently required material properties. As robocasting has just diverse applications among the many disparate materials classes such as metallic foams, pre-ceramic polymers, and biological tissues. This allows for a wide range of mechanical characteristics to be accessible through this technique, with additional trailing possibilities, use of ink fillers, and varying extrusion of process parameters. Filler effects. The micro and nanoscale filler materials are commonly used to create the composite material feedbacks for robocasting are available in a wide range of composition with morphological typical failing into the abroad characteristics of the sphere. The platelets and filaments tubes. The both composition and morphology play a significant role in the mechanical characteristics impaired by the fillers. For example, the inclusion of stiff boron nitro nanoabsorbs within epoxy feedback has been demonstrated to anticipatively increase overall composite strength and stiffness along the directions of fiber orientation due to sharp asymmetry. With the inclusion of hollow glass microscopation with small epoxy feedbacks has been demonstrated by isotopically improve the specific strength by significantly reduced by the total density of the composites. In addition to the shape, the differing the size resides within the fillers of the same morphological have been demonstrated to the yield of significant change in the mechanical properties. For epoxy carbon fibers composites for of identical composition, the flux resistance has been shown generally by decreasing with decreasing fiber length. Thank you.